Hi, my name is Haley Hollinshead, and this is my second semester organic spectra analysis video. So today we're going to be analyzing the molecule C8H9NO2, and the first thing we're going to look at is the mass spectrometry. So the spectrum here shows us quite a few different things. Right from the start, I can see that our M+ peak is going to be right here at 151. And in addition to that, we can also see that because it is the strongest peak on the spectrum, we can also note that this is also our base peak at this point. So the next thing I look at is going to be the degree of unsaturation of the molecule. As we can see up here, I already did that. I typed it out so it would be a little bit cleaner. This is our formula, 2C plus 2 plus nitrogen minus halides minus hydrogens all over 2. So when I plug in my numbers from the molecule, we get a DOU of 5. So that means we could have something like a benzene ring, which has a degree of unsaturation of 4 and a double bond somewhere else, or a different combination of things like that. So in addition to this, we can also note that we actually don't have any halides present in our molecule. We would see certain patterns in this if we were to have them, but we also have the molecule name, so we know there aren't any. And then finally, one of the last things I look at is the possible fragmentation patterns. So we can see we have one probably here and one here. So here we have M minus 74, and here we have M minus 44. And these don't directly line up with anything on our chart for fragmentation patterns, but most likely we're going to see that this fragmentation pattern, what's left over after that fragment, is the benzene ring that is most likely in this molecule. And I know this because the 77 indicates the molar mass of the benzene ring. So this is the diagram that we're going to be using to analyze our infrared spectroscopy in this video, and we're going to use this to kind of figure out what functional groups we might have present in our molecule. So the next thing that we're going to look at is the IR spectra produced by C8H9NO2, and we're going to be looking at 5 different regions here. So in our first region over here, which I've marked with the yellow, we're going to be looking for a few different things. We're going to be looking for things like alcohols, which look like a tongue, a amine, which looks like a vampire fang, an alkene, which looks like just one single V, or we could be looking for a carboxylic acid, which kind of looks like a beard. So as we see here, we do have a peak that is coming down, and it does kind of have that vampire fang shape, which can actually be a signifier that we have an amide there. And I can kind of tell that just based on how high the peak shows on our spectra, and so that probably means we have an N to H bond stretch there. If we move on to our second region, we are going to be looking for an indicator if we have a sp2 or sp3 bonds between our carbons, and because we see that this peak here actually falls above 3000 right here, and then we also kind of see these jagged lines throughout here, that means that we have sp2C bonds. So if we move on to our third region, which I've marked in the blue, we're actually looking for triple bonds here, so that's like C triple bond to C or C triple bond to N, and we don't have anything here, so we'll just move on to the next region. This next region, which I've marked in the gray, is where we will get a peak if we have a carbonyl in our molecule. And as we see here, right at the 1698 mark, we see that we have a carbonyl in the group, so that's C double bond to O. Now, this next little region here I kind of left to look at just because this is kind of the starting point of the fingerprint region, which we don't typically analyze at this level because it's really kind of hard to pick some things out there. But I can see that we have a lot of peaks through this region, which signifies that we most likely have C double bonded to C, and that those C's are probably in a benzene ring. We can also probably assume this just because I have such a high degree of unsaturation for the molecule as well. The next thing that we're going to look at in this analysis is the proton NMR for the molecule that we are examining, and this will help us determine the structure more formally. So the first thing that I look at when I'm doing proton NMR is I just do a quick addition of the integration numbers to make sure I have the correct number of protons in my molecule. So I know that I have 9 in my formula, so I just go ahead and take a peek. I have 2 plus 2 plus 5, so I do have 9 accounted for. The next thing I look at is how many neighboring protons are near the protons in question. So I go ahead and I do the n+1 rule. So doing that, I know that I have 0 neighbors near these 2 hydrogens. And when we move on to the next slide, I will do the integration numbers and the neighboring numbers for these protons, but because we need to zoom in a little bit to be able to see how many peaks they have. So while I'm still on this slide though, I can see kind of where these fall, what they might indicate on my molecule. So I predicted that there would probably be an amide on this molecule, and right around this area is actually where we would see peaks for an amide. So as we can see later in this analysis, I do predict that these 2 hydrogens here are the 2 hydrogens coming off of the nitrogen. So that would make sense because they fall right in this area where the amide would be listed. In addition to this, we also see here that this peak falls in the range of an ether, which is another group that I have in the molecule later when we draw the structure. So moving on to this closed-up version of the other spectrum, we can see a little bit more specifically how many peaks are in different areas. So this only accounts for the 7 protons that were not already examined in the first analysis. So we see here we have 2 peaks, and we then know that we have 1 neighbor to these 2 protons using the n+1 rule. Here we see that we have 3 peaks, and we have an integration number of 1. So that means that we have 2 neighbors to this 1 hydrogen according to the n+1 rule. And finally we see here again that we have another set of 3 peaks, and using the n+1 rule we know that these 2 protons will thus have 2 neighboring protons. So when I move on to my next slide and draw the structure, I will use this information to appropriately designate separate areas where my protons will interact and have different environments basically. So this is the structure I determined from the 3 spectra that I've analyzed so far. The first thing I'm going to do is show where these different protons are located in our structure. So we have 2 protons here with 0 neighbors. So these are the 2 protons coming off of the carbon in between these 2 carbons with no protons, or oxygen in that case. The 2 protons, which are the exchange protons, are the ones I predicted to be on the amide, so we see that that works out. We have 2 protons here with only 1 neighbor, 1 proton with 2 neighbors, and 2 protons with 2 neighbors. We see this adds to 5 here, so we know these are our 5 protons on our benzene ring. So we have 2 protons with only 1 neighbor, which would be these two up here. They only have one neighbor directly next to them. Next, we have one proton with two neighbors. So this would be this proton, and it has two neighbors here. And then we have two protons that have two neighbors. So these two protons have the two neighbors here, and then they both have this as a neighbor as well. And to coincide with this analysis, I also have used the IR analysis to determine what functional groups we had in this molecule. So I predicted that we would most likely have a benzene ring as well as a carbonyl group, and that carbonyl group would be an amide. As well, in some of the other shifts, the ether was also pretty apparent as well. And this structure also satisfies our degree of unsaturation, which is 5. We have 3 double bonds, which is 3, 1 ring, which accounts for 1, and then a double bond to an O, which accounts for our last degree of unsaturation, giving us a total of 5. So the next thing we're going to analyze is the carbon-13 NMR chemical shift. And I went ahead and put some of the values that are going to be shown in the next slide right here on our graph, just to kind of show how I labeled our different carbon environments. So the ones I just circled, those are actually our functional groups that I drew in our molecule. So here between the 60 and 70 we have the ether, and then between the 170 and 180 we have the amide, and then the rest of the carbons fall in this aromatic range, which we will see as I label the carbon environments in the next slide. So moving on to the actual spectrum produced by this, we see these different peaks which I labeled on the other graph. So this 171, that fell right in the range where we would see the amide. This 67 we saw was right around where we would see the ether. So that's how I labeled our carbons. Our first environment is obviously here, the amide. Our second environment, which is the carbon attached to the O, would be the ether. Our third environment, this carbon right here, which is also attached to the O, I have labeled here because although it is a part of the aromatic ring, as we can see it is a part of it, and it is pretty close to these other aromatic carbons, but because it is attached to the oxygen, it is downshifted a little bit farther just because of the electronegativity of the oxygen. So moving on, we see we have 4, 5, and 6 right here. So we have 4 right here, these two carbons. 5 is here with these two carbons, and 6 right down here, the last carbon on the ring. And the reason why they're labeled like that is just in order of how close they are to the electronegative atom oxygen. So that actually causes them to be more downshifted or less downshifted, which is how I can tell which is which. Well, thank you for watching. This is my second attempt at a spectra analysis video, and I hope you've enjoyed my analysis of C8H9NO2.